Hey everyone, how would you take a single state machine diagram and generate both Python and C++ for it? Those syntaxes are fairly different. How does that work? Well, that's the topic of today's video, and I will say that this is an advanced feature. Don't get scared off if you're new to StateSmith. You can follow the simple path, which are, check out tutorials 3 and 4. Um, but yeah, I also want to show other power users some cool features here, and I've been doing this for a while. All right, multi-lang 2, here we go. So there's some links in this, it's all online, examples. If you want to do this, check out tutorial 2 first, NCSX and IntelliSense, how to set that up. But here's the crux of the video. We've got one diagram. It's kind of like a very simple light bulb state machine where you can toggle it between off and on. And it just turns the bulb off, turns the bulb on, and then increments a count. Nothing too crazy. But if we look at the syntactic differences, some of them between C++ and Python, obviously there's semicolons or no semicolons. With C++, if we had inherited members, you get this implicit this, where Python always requires self, increment operator or Python plus equals 1, and then different casing for Booleans. Nothing too crazy. And I have solved this a number of times in different places, and actually for our large unit test kind of integration test suite, I do this same approach. So this is well supported. Right, so typically what I'll do is I'll choose a primary language, like in this diagram above, I chose C++, and then during code generation or just before code generation, I'll hook into StateSmith and translate something like do stuff with a semicolon to do stuff without the semicolon, or count plus plus to count plus equals 1, or true to capital true. And it's actually not that hard once you understand how to use C# scripts. Okay, and so there are different ways you could solve this problem. One way is to pre-process the diagram. So you could use like any preprocessor, take your plant UML diagram, do the kind of language translation, save it to a Python specific plant UML file and a C++ plant UML specific file. That could work. Totally valid option, but I wouldn't try to do that with a draw.io diagram, especially not the SVG diagrams, because they are like base64 encoded, and some of the XML diagrams actually are compressed too. So the pre-processing route, which I'm not showing here because people can figure that out easily on their own, is really only applicable to plant UML. So let's go to a solution that works for any supported diagram, plant UML, draw.io, or the older YED ones. So what we're going to do here is we're going to hook into the transformation pipeline of StateSmith and add our own custom transformation step. And so this code here, we get access to the pipeline, and we insert in place 0, so right at the front, our custom transformation step, where this is a lambda if you're unfamiliar with the syntax, just saying, okay, we get a state machine object here, and here's kind of the body of the function if you haven't seen C# lambdas before, or lots of other languages have lambdas like this too. And so inside of this function, that's part of the transformation step, we say, okay, state machine, I want to visit you recursively, and we're going to use another lambda. And this allows us to have another tiny little function here where for every single state machine vertex, we get this basically like a callback. And so within for each state machine vertex, we visit the behaviors that vertex has. And all we do is say, okay, for each behavior, we're going to take its action code, take it from C++ to Pythonify it, and same thing for the guard code. And we're just doing a very simple Pythonification from C++ to Python. Just strip out semicolons, change plus plus to plus equals 1, comments, and then casing for Booleans. That's it. That's worked for all of my basic needs. I should mention too that if you had more advanced needs, you could actually use the StateSmith grammar to parse the action code here and the guard code to figure out like, okay, I don't want to replace semicolons and strings, so you could use that grammar to treat strings differently than a regular semicolon. that's possible. We'll just briefly touch on using composition instead of inheritance can be helpful. And when you're choosing your primary diagram language, I find it's easier to use the most picky or detail-oriented language like C++, because it's easier to translate from something that has more information and kind of strip out that extra information like semicolons, rather than to start from the opposite like Python and try to infer when you need to add semicolons. So yeah, some simple tips there. Okay, let's open it up here. And when you first open up the repo, like those other tutorials will say, do not install C# devkit. Yeah, there's a lot of reasons for that. One of which is that C# script files are not supported by devkit. And that's in those links at the top of the README. So let's close that. And so yeah, when you first launch this, you're going to see something like this. We've got a directory for our C++ generated code and handwritten code. We've got a Python directory for some handwritten Python code and generated code. And yeah, let's get this C# script file working properly first. So first what we're going to do is go sscli, enter. And we're going to use our arrow keys to set up VS Code for StateSmith and CSX files. Now, we don't care about draw.io in this situation, so we're going to just pick VS Code C# script debugging IntelliSense. So we'll hit that. And it basically does the couple manual commands for us, but it still isn't working yet. So what we're going to do is use this command here. So I'm just going to copy that, OmniSharp, restart OmniSharp. And I'm going to go Control-Shift-P to open up my terminal window, or my, VS Code command palette, and restart OmniSharp. Now that's going to take a couple seconds. You can see the kind of syntax highlighting changed. But in a second or two, we should see it. And if you have problems with this, you can click on Output. And this is documented fairly well already, but if you click on OmniSharp log, if you are having issues, this is where you kind of get more information. But we don't need to worry about that for now. So I'm going to close this. And if I hover over this, yeah, you see that I'm getting IntelliSense now. You can see that like I can click on this and it's figured them out. I can refactor these. We're all set up for IntelliSense now. And there's tutorial videos and wiki links to help you get there. Okay, so first thing we're going to do is just walk through this a tiny bit. So we bring in StateSmith 0.17.5, which is the latest as of today. And this is the StateSmith library version. The library version and the CLI have two different versions because they move, semi-independently. So if you look at NuGet.org, this is the package manager for C#. This is how StateSmith originally started. We didn't have a CLI. We had a NuGet, like a kind of library package. And so some users, like when we first launched, this was the only way to use StateSmith. It has been downloaded 50,000 times, and periodically there are big burps of, I guess people probably either upgrading or using this on their CI/CD system. But like at some points we had people like 30,000 in like 1 month here. So we define our diagram path here. So it's just light sm.plantUML, and we can see it right there. And then we've got two classes here. We don't need these classes here. This is just a nice way to organize things together, keep the C++ stuff together, keep the Python stuff together. You can do whatever you want here. Right. So if we look at the CPP gen, there's a generate method, which just gets a state machine runner. It says, okay, here's our diagram path. Here's our render config down there. And we want to transpile for C++. Then we also say, okay, runner settings output directory CPP, so that we can generate it into that directory. And then we turn on the simulator generation too, so that we get a sim.html file. By default, if you don't do this, then you won't get it. If you're using just the CLI tool without CSX files, we enable it by default. So it's just kind of different options. Here you have to opt in. In the simplified workflow, you have to opt out. And then we say run. The render config here is pretty simple. We just say, okay, we are going to have inside of our state machine a variable called of type light bulb, and we'll call it bulb. And that allows us to refer to it like in our diagram. Where was it? Right here. So we can say bulb.set. So that's how we can say bulb.set and have it actually translate to real useful code. And we put it in our auto expanded section here. And it just does two things at once, which you can see in the tooltip there. It allows us to define a variable, put it into our auto expanded structures, and then creates expansions so that we don't have to write something like sm bars.bulb or something like that in our diagram. We can just write bulb, and StateSmith will figure out the path for us to that variable. And then for that to work, we just need to say, okay, include this library into our generated files so that we can actually get access to that type. That's it. Nice and simple. So now what we're going to do, though, is go down to the Python code gen. And the Python code gen is very similar. Starts off the exact same, except we say we want a transpile for Python this time. And we say output directory is py, and we enable our code generation for this. But I will note that the simulator file, like the .sim.html file that's generated, currently does not support our custom transformations yet. So that'll come at some point. If you need that, comment on that issue and I'll try to prioritize it. But I think it's a little bit of a niche case for right now. So there's other things I'm going to work on first. Anyway, so we set up our settings and then we say, okay, Pythonify the diagram behaviors, which we'll touch on in a second, and then we say run, which will do the actual full code gen and everything. The render config for Python also has an auto expanded variable, slightly different syntax because it's Python. Self.bulb equals, a new light bulb. And then we have to do an import so we get access to it. The actual light bulb class is handwritten Python code, just like the light bulb header file for C++ was handwritten. Okay, so far so good. I hope you're all with me. Okay, so now we get down to Pythonify the diagram behaviors. And we're actually going to set a breakpoint here. Now because we set up VS Code to work well with this C# script file, I can set a breakpoint now. So I actually have one here. So all I'm going to do is hit F5. And we're going to start debugging. Well, first did I set a breakpoint there? I did, I guess. Oops. Let's hit F5, or I guess, be a little bit more visually supportive if I click the button instead. Okay, so it did the C++ code gen, finished normally, and now we're into the Python part, and we hit a breakpoint. So we can look at the action code, and we can see that it still looks like C++. We got a semicolon, and we've got a lowercase false. So I'm going to step over this. We'll see that it runs our Pythonify diagram code, and we'll check it again. And here we got rid of the semicolon, and we've got a capital for false. But you can do other more advanced stuff too. Like you can, if you wanted to do something deeper, like we can look at the behavior structure here, where we can see, well, we've got an enter behavior and we've got a transition behavior here on the behaviors. You can look at the vertex itself and basically inspect it very deeply, or you could look at the actual state machine itself. So yeah, it's debugging is really helpful if you're going to start to do anything kind of fancy with transformation pipelines. Then yeah, we can just take off that breakpoint and run it, and we're good to go. Now you don't have to always run it like this. You can, if you want, still run sscli like normal. So we'll just run it here and we'll say watch. And so you can run this normally, and now it's watching all of these files actually here. So if I make a new line here and save, we'll see that it picked up the change. So it's It's noticing the CSX changes, but it also checks the, oops, I saved again. It also notices changes to your plant UML file. So any of the dependencies, when they change, it'll keep running. So that's the majority of what I wanted to show off. The last thing I'll just loop people into if they're interested is where our specification tests are. So if you go to StateSmith source, StateSmith test, specification tests, 2 is where the big ones are. So if you go to spec2sm.graphml, you'll need the YED editor, this guy here, to be able to view it. It's free, not open source, but free. And it's still supported, but I don't really push people towards it because it's got some quirks. If you're aware of the quirks, it's okay. But yeah, so in this one large state machine, we have a section for do event testing, regular event testing, behavior ordering, parent-child transitions, and inside of these, we've got other tests here, and basically what I do is that for every single language and for every algorithm, it's kind of this like large multiplication factor. I use the exact same specification tests with some kind of like special processing to make it work for all the different languages, and the same diagram, because it's too much work to manage otherwise. I need to have one single source of truth that works in one suite of tests to make sure that it works for all the different languages. And yeah, so that's what I do. Yeah, hope you enjoyed that. Let me know if you have any questions, and happy state machining.